So yeah, Marta, probably let's start the broadcast.
Okay, yep.
So thank you everyone for joining today. We continue our sessions called R&D Talk. There is already a third session, and those sessions are dedicated to share some deep technologies, trends, and insights. And today's one would be dedicated to really frontier of the innovation for quantum computing, for quantum at all. And our today's speaker is Damir Khadiyev. He is R&D science practice lead who has established the quantum expertise inside the SoftServe and developed it to the current state as is. So I believe this talk would be really insightful to understand what is quantum computing and what is not. And as Damir mentioned, without a single math equation, we understand like place of quantum technology in overall innovation landscape and its today's application for the industry, and like have a look what are the disruptive use cases and how we can present those use cases to our clients. So Damir Khadiyev, nice to meet you. Before I give you the word, I encourage you to ask the question during the session. We will have the time in the end to like answer all of them, both here in Zoom or on the workplace. And yeah, Damir, stage is yours.
Hi, everyone. Thank you, Bogdan, for this kind introduction. Let me start sharing the screen. And... So, do you see it now?
We currently see it's not in the sharing mode. We see like some settings mode. So probably you should start to share one more time.
Yeah, started. 1 second. Me and sharing. No, okay. Are not best friends. So now it should be better.
Yeah, it is.
Okay, good. So as Bogdan introduced me, my name is Damir Khadiyev. I'm a science practice leader, and also I worked a lot in quantum computing. It happened to me that I'm a physicist as well. That's why it was very, very lucky for me to find this kind of job in the enterprise company and do some things that are related to science. So today I'm going to talk about quantum computing, and overall presentation is separated to 3 different sections. In the first section, we will try to define how come that we are using quantum, what is quantum physics, and like what is the nature of this phenomenon in general. Then we will look to the transition from quantum physics to quantum computing. How can we ever even perform computations using some principles of quantum physics? And at the third stage, we will speak about some business things. Why do we have quantum computing instead of SoftServe in general, and how we would like to talk about it with our existing or maybe new potential customers that we would like to have. As Bogdan mentioned, if you have any questions, please feel free to ask. Maybe you can stop and interrupt in scientific manner. We will try to reply to any question out there. So first things first, it's what is quantum? And I'm going to start from a very beginning. During the first section, I will name some concepts that are physicals, like atom, electron, superposition, entanglement. Please don't take them too close to your heart. It's not a prerequisite to think about quantum computing to have deep understanding of physics. However, we will have to mention them to understand why quantum is so unusual. First thing is to understand why do we have word quantum in general. It comes from Latin. In Latin, quantus means how much, and that's it. First appearance of its plurals, like quanta, was mentioned in 17th century in some scientific books when it meant like portion, piece of something. And basically this general sense goes to the modern physics and to modern computer science with quantum computing as well. So in the very beginning of 20th century, very talented physicist whose name was Max Planck, he worked on the next problem. He tried to observe the properties of the bodies that are heated. you can imagine if you hit different materials, most likely they will shine with different colors. And this is a very unique observation because basically it depends on some internal chemical structure, but the chemical structure also depends on properties of quantum physics that will be discovered in future. Particularly, he tried to study black body radiation problem, and black body is some kind of body that tries to absorb every radiation that goes on top of it, and do not repeat it back. It doesn't have any reflection. And you might be surprised that actually our sun is a perfect black body, like almost perfect black body, because its outer area of the sun just absorbs every radiation that goes to it. However, it's not black at all, but it's just called black body. What Max Planck discovered that somehow during this heating, the energy can be absorbed or released from this body in small packets, and those packets lately were called as quantums. And overall idea of quantization is a hypothesis that tells you that you can have a physical entity that can obtain only discrete values. And the minimum amount of this value of some physical property of this physical entity is called quantum. How can we imagine like difference between continuous values and discrete values? Imagine that I'm driving a car, and if I try to drive the car, I try to record speed of my car at any moment of time. For example, if I will measure it every second, it will take like 0 kilometers per hour, then like 10 kilometers per hour, then 15 kilometers per hour, then 15 and a half. And then if I would like to make it more granularly, so for example, I would like to measure the speed at every millisecond, it will be 0 kilometers per hour or 0.05 kilometers per hour, 0.07, etc. So it doesn't matter how small step you take, you will still get some real value of speed that is kind of continuous. However, if we are speaking about discrete values, imagine that the minimum step of my speed change can take only 10 kilometers per hour. And if I would measure it, it would look every second, like 0 kilometers, 10 kilometers per hour, then 20 kilometers per hour, then again 10, and that's it. So it would look like result of multiplication of some small value. The smallest value, as we agreed, is 10 kilometers per hour, times some integer, 1, 2, 3, or 100, if I can achieve the speed with my car. So first interesting observation that is found in area of so-called quantum physics is that some physical properties, they can contain, they can obtain only discrete values. Then in the beginning of 20th century, people started looking for deeper structure of the elements that are surrounding us. Let's agree, right, for this moment, that our Earth is not flat, that this planet turns around the sun, and also that all of us consist out of the atoms. However, in the beginning of 20th century, there were many people who didn't believe that we actually consist out of the atoms, and they required some proofs that it actually happens. While other scientists believed into this concept, and they tried to understand the inner structure of the atom, what is happening inside of that. Actually, at this very same time, many people still believe that there are angels behind the planets that making them move around the sun. That's also kind of fine observation that some frontiers of technology were that far at this moment. However, another ones were not that far at this moment. So one of the critical events that happened during this time was finding the electron. At 1897, Joseph Thomson was able to extract the electrons as the particles that are responsible for charges. And he started thinking about the structure of the atom. First, he imagined that our atom looks like a plum pudding. Basically, that we have some structure that is positively charged, and that electrons are like raisins that are inside of them. However, another scientist, Rutherford, tried to challenge this idea and made some experiments. And during these experiments, he got to the idea that maybe electrons inside of the atom could look like our planet turning around the sun. And that's why you got this model of an atom that was called planetary model. This looks reasonable. The only problem that atoms would be very unstable in this situation, because there is a very fundamental law that says if there is a charged particle, this particle will lose energy. It's also pretty intuitive to understand. If I will run around the Wrocław office for quite some time, In 2 hours, I will start losing my energy, and you will find me somewhere fallen on the kitchen on the 7th floor here, because I will be out of my energy. Same thing goes with electron that is losing his energy to radiation, and inevitably it will fall to the core of the atom. But this is not happening. We are not evaporated like people in Avengers, right? We still are stable. We are not falling through our chairs. We are there. Then another scientist, Niels Bohr, suggested 2 postulates, saying that, first of all, electron can be only in one certain position, and it can change this position, this orbit where it's placed, only by absorbing or releasing some discrete value of energy. That somehow correlates with the fact that we've got on the previous slide with Max Planck's discovery. This feels very counterintuitive, right? That for some reason, electrons start behave differently from what we would observe in the real life with the planets turning around the sun. However, of course, there is a different nature between those 2 systems, but it still felt very, very unnatural. So the first unusual fact is those stationary orbits and discrete values of energy, something that we haven't observed before. Next thing, if we see some special properties of the electron, we would like to understand how it moves inside of that. And that's a very challenging question as well. In physics, actually, many things are related to prediction of movement of different things. If I have a ball and I would like to throw it somehow, if I know its initial position, its speed, and the vector of this speed, most likely I will know where this ball will be in the future. And the path that this ball will take is called trajectory. You can make a very simple experiment. If you're brave enough, if you have old microwave and you can make some kind of chamber, you can make the thing that is called cloud chamber. Basically, that's a reservoir that contains some vapor, not water vapor, but some vapor of some element. And if you will throw particles through this chamber, you will see the tracks of condensed vapor where this particle came. And it looks pretty reasonable, right? Even on this screenshot, you see that there is a source of those particles, and you can definitely see the tracks of those particles. You know where they started and where they go. However, if you would like to look closer, if you would like to investigate this trajectory, like on a very, very precise level, you will see that particle appears in one place, then it appears in another place, and then it appears in another place. And it doesn't look like a very good continuous distribution. Then people started thinking that might be there is no sense about thinking about trajectory for those very small objects. And they decided to invent all this probabilistic theory around the movement of the quantum particles. This principle that doesn't allow us to measure things very precisely simultaneously, like, for example, the coordinate and impulse or velocity, as one would say, at the very same time, is one of the fundamental properties of our universe, and it's called Heisenberg principle of uncertainty. So that's the second observation. We have discrete values. Another observation that we cannot measure some discrete values simultaneously, and it's very hard to speak about trajectory in a classical sense as we used to before. Then things go even weirder. Imagine next setup. For example, you have some screen and you have some gun that can strike with paintballs. And before reaching the target, you have to throw it through the slit. It's obvious, right, that if you're throwing the balls, you will get the most of the hits on the screen that will be totally oppositely located in front of the slit. And the same will happen if you will have 2 slits. And if you will, for example, strike them one by one through those both slits, if you would, for example, keep one closed or the second one closed, you will see 2 lines on the screen. This feels natural. However, if you will look to the same setup, but you will use waves, for example, of water. And on the screen, you will try to measure the intensity of the wave that is hitting the screen. You will see a very different picture because waves, they can interact one with each other. And when they interact, the intensity will be shown as lines on the screen. This thing is called interference screen, and this is something that is fundamental to waves. However, people tried to make this experiment with electrons. And what they saw is that electrons behave like waves when they go through this through this double slit experiment. And it felt very unnatural because before that, people thought that, okay, if I'm going to throw an electron, that's a particle, it should behave like a particle, like a normal one. However, we can see that under some conditions, objects like electrons, they can both be waves and particles. That's also very unnatural situation for us to understand, even after all these years. However, things can be even more weirder. If you will construct such experiment that will track each particle going through this double slit experiment, you will see that electron, just by this observation, might start behaving as a particle again. And it means that even the fact how we observe quantum system, how our classical brain, how our classical system interacts with quantum system, changes the behavior of the quantum system. This is also not something that we used to see in the real life around us. And there are two even more beautiful and fundamental behaviors that we can observe in the quantum world. One of them is called entanglement. Entanglement is a state of deep relationship between two objects that came, for example, from the same source, from the same physical experiment, or if they interacted in a very special way. And they behave in that way that if you will take one piece and then move another piece far away, it doesn't matter how far away. And if you will change one of the pieces of this entangled system, the second one immediately will change its state itself. It means that for some objects in the quantum world, we can have very non-local experiences where, like, it doesn't matter what is the distance between those two objects, but without violation of causality and maximum interaction speed of light, we can see that those objects are still somehow related. And this is something that is exploited in quantum networking, right? This is a beautiful idea of communication using quantum technologies. Another thing is something that was demonstrated in this previous experiment. If single electron goes through this double slit experiment, how come that we can see this interference picture on the screen? Well, it's explained that from the probabilistic point of view, this electron goes through both slits simultaneously, and it interacts with itself, and then you see this wave-like behavior, something that is very, very also unnatural and very unusual. But what does it mean? It means that this electron was in both positions simultaneously. So entanglement is a deep relationship between objects that, like, it doesn't matter what is distance between those two objects. And another thing is ability to be in multiple states simultaneously. Usually people mention Schrodinger's cat, right? You have a box with a cat, but I don't want to go to this example. Most likely you will be able to figure out somehow. Next slide. Why was it important? All the developments in quantum physics allowed us to have iPhones, because all of this is foundation of all the microchips that we have. It allows us to have solar panels, and it allows us to reduce our carbon emission and to achieve some ecological milestones. We wouldn't have MRI, we wouldn't have clocks in GPS, we wouldn't have laser-based emitters in our communications. So the importance of those properties that were found by scientists in the early beginning / like up to mid of the century, they reflect everyday life of every person who attends this call or who doesn't attend this call at all. Now we need to think about quantum computing. I believe that most of you already have seen Oppenheimer movie. The overall Los Alamos project, where people worked on the nuclear weapon, was very important for overall development of science and technologies. For example, there were people like von Neumann or Stanislav Ulam who worked in the Los Alamos project, and they made the foundations of Monte Carlo simulations or there were remarkable scientists who impacted the research areas and technology areas all over the world. But actually, there was one guy who even was mentioned in the movie, but he just wasn't doing anything by except playing a bongo, who've made the foundations of quantum computing and the fact that we have this call with you guys today. So now we are going to quantum computing from quantum physics. And the person that I mentioned was Richard Feynman. Richard Feynman basically is one of the most famous popularizers of science in 20th century, except the fact that he was outstanding scientist and he was able to imagine things that is very hard to imagine to a regular person. However, he came to conclusion that nature isn't classical, and if he would like to make any simulation of this nature, this thing has to be quantum. So basically, if we want to simulate the behavior of the smallest thing in our world, we need to somehow make the calculational things that are capable to perform those calculations. Basically, he said that at IBM's conference, and as you see, they took his words very seriously, and now they are kind of one of the largest manufacturers of quantum computers around the world. So what is quantum computing? Quantum computing is just a computational technique that utilizes principles of quantum physics to perform the calculations. Usually you can hear the word qubit. Qubit is just a basic unit of quantum information. Like in the real life, in the classical life, you can meet bits, things that can be 1 or 0, two-state systems. You can find a qubit, and qubit also can be in two states, in 1 and 0, but also he can take multiple states in between of them. Also, one qubit can be entangled with each other. This is something that I shown you before. It can be deeply related to the state of different qubit, and also it can be in multiple positions simultaneously, in multiple states simultaneously. Sorry. But once you will measure it, once you will perform this interaction from like classical system with this quantum system, it can be resolved only to state 1 or state 0. That makes it really natural to think about qubits as foundation of computational systems. And quantum computers, basically device that is capable to implement those qubits or not qubits, or utilize some principles of quantum physics to implement some different systems to perform computations. But most likely it's like system that is capable to implement those qubits and make some operations over them to perform the computations. Why should we think about quantum computers in the first place? Well, the problem is next. If you would like to make a simulation of any quantum system, it will take enormous resources. And those resources, they grow exponentially. It means that if you need to simulate, for example, behavior of 5 qubits, you need 2 to the power of 5 memory resources for this thing. And if you would like to simulate larger systems, and if you will think about realistic large systems that can have like multiple particles, like thousands, tens of thousands of them, and even more, up to 10 to the power of 23, you can understand that nothing in the world, not any supercomputer will be able to perform those simulations. Another thing that maybe you've heard about is Moore's law. Basically, that size of semiconducting entities that we have in our computers and our cell phones is decreasing with years. But we are going to some threshold in size of the system where we will see a lot of effects of quantum computing. However, this can be a pretty questionable statement because people made 3 nanometers technological process right now, and they can go even deeper and deeper. So we will see how it goes. However, maybe after some limit, we will have to deal with quantum effects in our computational techniques. You will say, all of that is beautiful, but all of those things are for scientists. Maybe like some physicists or some people who would like to know more about it would bother with this thing. Or some people will make those devices and it will make it easier for everyone. Why there is some noise about quantum computing in overall industry for the last 5 years. So after Feynman's idea of using quantum computers to describe the nature, there were many scientists who tried to find some other cases of usage of quantum computing. And they came up with very interesting solutions, like how to search in unstructured database, how to make prime factors of the integers and use it for decryption, how to encrypt the data using quantum phenomena, and all the other interesting things that are not related to quantum physics directly. And this was brilliant because for some cases, quantum computing was able to provide quantum advantage. Quantum advantage is ability of quantum computer to perform certain things much faster than the classical computer. And this idea was fascinating, and it was taken by many people who were happy about all of this idea, and they started setting the false expectations out of this technology. Let's review some of them. First of all, there were claims that quantum computer can be at every home. This is not happening, and this is something that wouldn't happen at all. Quantum computing is a tool that is able to solve some specific problems, rather than trying to solve every problem just faster than other ones. There was a statement that quantum computing is able to solve the problem of global warming in the world just by introducing the quantum computer. This is also not true, and it's very easy to fall under these false expectations and then say that quantum computing is something that is not realistic. And we have two views. We have scientific view, in which there are scientists who say that, okay, quantum computing, let's make quantum computing only for physicists, for some research industry. And also there is speculative view that tells that quantum computing will have help everyone. Where is our place? Where is place of SoftServe? We are in the industrial view. We are a little bit more optimistic than scientists. However, we should be critical about all the speculations that are there around quantum computing. We have to be in the middle, and that's our point to go and educate our customers, to educate business, to educate industry that is not aware of quantum computing. How can it actually help them, rather than saying that, okay, we can make quantum computing for you and this will solve all your problems and will reduce all of your costs simultaneously. There is another point about quantum computing, that quantum computing is just a buzzword like NFTs, if you remember still about them, or maybe if you remember about segways or any other technologies that was hyped and then it was not needed by anyone. Well, first of all, you need to go to previous chapter and check the expectations. If you think that quantum computing is a universal tool for everything, then most likely you will get to this valley of quantum winter where you wouldn't believe that quantum computing can do anything. Then quantum computing stands on shoulders of giants, right? We had 40 years of very solid research, and this research continues currently. For through last 2 months, I've seen 4 papers from IBM fellows digging deeper and deeper into quantum technology to make their hardware much better. And also, we all stand on those brilliant people who invented the foundations of quantum physics. Also, quantum computing hardware already achieved outstanding milestones. Imagine that we're using single particle of light, not particle, like single quantum of light, the photon, to perform the calculations. Imagine that you can put single photon into the grid of the atoms. You can control its state completely. You can make it interact with any photon in the grid, and to make it calculate for you as a calculator, basically. Not a calculator, but a system that is capable to perform the computation. And this is exciting on its own. Also, it's inspired already many other technologies. For example, to make those photonic quantum devices, people made very precise light sources being able to deliver that single atom, or sensors that are capable to feel every single atom within this grid. And that's also outstanding because we never had this control over the matter in our life. Then you may find a lot of where people apply quantum computing to different areas, like, for example, to ray tracing or quantum blockchain or whatever that you can find out there. But that's just curiosity-driven research. It doesn't mean that it will help anyone. People just want to use this new tool to address some problems. And of course, we just don't know what we can uncover from this activity. And of course, if all the expectations from quantum computing wouldn't work, this is the worst case scenario. We don't have any other option for physics. We will still have to bother with this thing, and it will still remain as a part of our scientific landscape. Okay, So I think I'm going to skip some of the slides in favor of time because they're philosophical, and let's go to why would industry seek for new ways to perform computations? This is part that might be relevant for you. First of all, quantum phenomena might be important for their value chain. For example, Toyota works extensively on design of new materials or on optimization of their batteries because they want to achieve their milestones in carbon reduction or in whatever other area that is important for them. And they have to deal with chemistry, they have to deal with very complicated problems, and quantum computing can be a disruptor out there. That's why they focus their efforts of their R&D teams to work with quantum computing. Also, another scenario that business already uses traditional high-performance computing, and they would like to improve the way they work with their daily operations. This is the case for financial sector, for retail, for logistics, or for energy, where they have to perform those very heavy on computation, on computational power simulations, and they need to increase them, to make them somehow faster. And then quantum can help to them. Of course, it's security. Security is a critical domain for everyone. And with this possibility of quantum algorithms to break modern encryption, it becomes a real threat to overall security, because even though we don't have those devices right now, we might have them in 10 years, and all the encrypted traffic that can be like mirrored right now can be that easily basically decrypted by the quantum algorithms. Also, there are people that are just curious, or they received some kind of false expectations, and we as their partners, we can talk to them and set proper expectations from the technology. So when people are in industry looking for quantum computing, they're looking for quantum advantage. As I mentioned, that's ability of some of quantum devices to solve and address some certain problems more efficiently than classical computers. And you can think about complexity measure metrics, that is maybe like O notation, something that you've heard before, but this is never enough, because it also depends on the level of development of quantum and classical hardware. It depends on the actual implementation, on the system design of the applications that actually runs, and you cannot just easily put quantum computer in there. You will have to think about this design to address the problem that even have some mathematically proven computational advantage. Here you may see some areas where quantum computing can help, and we can go to this thing a little bit in detail a little bit late. And also what we saw already is proofs of quantum supremacy, of quantum advantage, that are maybe not that relevant for industry right now. However, they are very relevant as a milestone for quantum computers. Basically, they were able to simulate some physical systems that would be impossible to simulate using classical computing. At least they claim so. And we cannot check it because we don't have like powerful enough classical devices, and we don't have quantum devices to do so. However, we believe to academic community, we believe to scientists and hardware providers that those milestones were actually achieved. Here is typical milestone for quantum development roadmap, and this is something like that can vary from one provider of quantum hardware to another. However, for IBM is one of the most reliable because they met most of their milestones, and you see that they have a very clear roadmap until 2026, where they plan to show very good utilization of their quantum devices. Currently, they've built this 400 qubits, meaning that 400 computational elements system, and this thing already can show some beautiful results, and they published publication on this thing this summer. It's also related to physics, but it opened the doors to some optimization techniques. It opened the door to some simulations in chemistry or in the material science. Will you excuse me? I need to plug my laptop into a charger. I hope that this will not delay the presentation significantly. Just a second. Do you still hear and see everything?
Sure.
Sure. Okay. Thank you so much, and I'm so sorry for interruption. So here is report from our good partner and colleagues from McKinsey. They constantly monitor quantum computing hardware and software landscape, And here you can see some insights where quantum computing will have the most relevant impact per industry or per area of computation or applied problems out there. You will see that most disruptive cases will be introduced in areas of energy, of chemicals, of pharmaceuticals, where you have to deal with objects that actually have some internal quantum nature. Also, we will have some impact on finance because we are speaking about some kind of optimization problems or simulation problems, and quantum computing can bring very good value to this thing. However, you might see that it shows good impact for energy like oil and gas industry or for automotive, aerospace, and feel free to read their technology monitor and you will find many interesting insights about like quantum computing industry. That might be a little bit overselling, saying that quantum computing can do a little bit more than it can do in real life. However, it's very important because people are listening to companies like McKinsey. They invest more and more into quantum computing, and it inevitably makes this boost of technology that fast. So up to our opinion of our team, if we will try to range the impact of quantum computing to different technologies, we would say that the highest impact will be for material design, something where we need to deal with chemistry and optimization, something that I mentioned before, in simulation and optimization, in solving partial differential equations that can be very relevant to many industries as well, of course, to science, but it depends on every actual applied problem out there. And another thing that happened last year is first production usage of quantum computing. Basically, there is a case provided by a company called SavantX in collaboration with provider of quantum computing hardware that is called D-Wave, where they optimized cargo processing in Port of Los Angeles and improved it significantly. Of course, we need to take this use case with a pinch of salt because it's a hybrid model. It can combine some classical optimization with quantum optimization. And in our private talks to those guys who implemented this on hardware, we can do the same state-of-the-art solution on our own. So if you would like to solve the case that is similar somehow to logistics or optimization, know that within our team, we can do the same, and it will be on the same level as first production usage of quantum computing in the real life. So I will skip this science and industry alignment. Also in favor of time, I will share this presentation with you. Now let's speak about our team. Our team started 2 years ago. We can find up to 15 people within a company who are quantum computing experts. We started from the quantum incubator. That was a great event in Lviv, where we got many beautiful people that are currently the core of our quantum team. Also, we have some good partnerships with AWS, NVIDIA, with Ivan Franko National University of Lviv, where we collaborate with all of them to deliver best solutions in quantum computing area, to pass them as services to our customers and to figure out something new. Also, as a continuation of our effort of educating people to quantum computing, we run a thing that was called Quantum Bootcamp in Singapore. That was 8 weeks summer program where we tried to teach students, but also we asked them to look into the real use cases that were provided by 4 companies, by DBS, by Capel, by Cisco, and by Thales. And those 4 companies provided their real use cases, and we worked on them and presented to them, and they see, some of them see the value of quantum computing as important technology. And I hope that we will find something new out of that in the near future. And also for you to understand how big this event was, we had 7 quantum partners, including NVIDIA, AWS, IBM, Xanadu, the providers of hardware and software who believe that this technology can emerge with our company together. What we do inside of quantum R&D. We perform fundamental research. It means that we do have scientists who try to push boundaries of current research in quantum computing, addressing some fundamental problems of quantum computing and also of quantum physics as well. We work on algorithms development. Basically, when we go through the list of different use cases that we would like to identify for quantum computing, we try to implement every quantum algorithm that is necessary, that is feasible, and to put it to our library of the algorithms. Also, we interact with hardware providers like IBM or for example, hardware providers that are available through AWS Bracket to understand the benefits, pros and cons of different quantum computing hardware devices that we can find out there. We do consulting and workshops. And I mean, seriously, if you have any customer that is curious on quantum computing, come to us and we can consult them and we can make workshop. And this is something that is very interesting. We do system integration. It means that we collaborate with hardware providers, and with those hardware providers, we try to understand their frameworks, their tools, to use them effectively for any other people. We do education and community. And thing that we do that last but not least is R&D service. Basically, if some company doesn't have enough R&D resources, they can come to us and we will try to address their research problem exclusively. Currently, so far, if you will look to the map of different use cases and tools that we are using, we were focused on manufacturing and logistics previously. We worked on healthcare and life sciences because our quantum team is deeply related to life science teams that we have at R&D. Also, we looked into finance because it's one of the most disruptive, use cases of technology can be found for finance. We worked for agriculture and environment, and the next milestone for us will be networking and cryptography because it requires very hard domain knowledge. But after this collaboration with Cisco during Quantum Bootcamp, we are thinking about joint projects that we will try to complete during this year. We basically tried different tools to address those problems. We looked into quantum machine learning. Basically, imagine any network or architecture out there that is used in ML, and almost every variation of this algorithm can be put to quantum rails to some measure. And we try to investigate where quantum machine learning could behave better to a measure, of course, and availability of our devices, and where it behaves worse than any classical algorithm. Also, we looked into the simulation, something that is devoted to any Monte Carlo methods or time series predictions, or if you need to make some computational resources estimation to perform those simulations using quantum computing, this is something that we do. And last but not least, it's optimization problem. Those optimization problems are from very different domains. They can be from logistics, from retail, they can be from finance. And what is brilliant about those problems, they are very complicated to be solved by classical computers. So for example, if you will go through one of the use cases of pre-production vehicles optimization that will be shown later in the presentation, you would need 80 minutes to perform just one single optimization with half of parameters that are needed. And for example, if you would like to make oil rig simulation, fully featured oil rig simulation to make it basically physical digital twin, you might need up to 2 years to obtain this simulation. And quantum computing can be something that might help in this area to make it a little bit faster than it would like. Anything that is better than 2 years is always better, right? I can skip areas of research so far. Here, I would like to highlight how we perform this transition to quantum. First of all, we need to identify proper use cases. We need to find the most computationally challenging problems. I mean, the complexity of the problem should lie not in the amount of data that you have. It should lie in the computational complexity, how hard, how time-consuming and resource-consuming this problem will be. And another thing that we need to understand that this problem should be available for the end user, not using quantum computing just for using of quantum computing. Then we map it to the mathematical problem, where we try to define mathematical problem that can be formulated for almost every problem out there. This helps us to understand the complexity and resources that we need. Then we evaluate the classical solution, its properties. Then we make the first preliminary feasibility study where we try to understand which quantum algorithm can we use. And then we go to proper fully functional feasibility study that usually takes from 1 month to 3 months, where we try to address exact specific request that we try to solve with quantum computing. We give a very good and accurate resources estimation and timeline for this thing to be actually implemented and then plugged into the real life. This transition to quantum computing can be somewhat complicated, right? Different use cases can be mapped to, for example, same or different mathematical classes of problems. They can have different computational complexity, and moreover, you can address those problems with different classical or quantum computational tools. And it's usually our responsibility to figure out which tool to select for which problem, or for example, which flavor, which mathematical formulation of the use case can be beneficial to apply quantum computing to that. And sometimes you need to understand that it might be totally neglectable in terms of computational complexity to formulate the problem for quantum computer. So you need to be very, very accurate about this thing. Next. Use cases. So here I would like to just briefly share some use cases that we dealt with at our quantum R&D. I will start from financial story, where we try to use quantum machine learning to make predictions of the asset price using some news from market, basically some social media feeds, news feeds, correlated assets. And what we observed that quantum machine learning model is capable to catch nonlinearity slightly better, that those models, they are able to train faster per epoch than the classical models, and they are capable to understand this nonlinearity faster. But maybe it's the cost of the training time, just because we don't have this hardware yet. We investigated derivatives pricing using different approaches. You can do it using one of the traditional quantum computing methods to address it. It's called quantum amplitude estimation. And this thing mathematically prove, like with mathematical proof, gives ability to solve this problem quadratically faster. It means that instead of 1 million of operations, you can have only 1,000 of operations, and this is a significant boost. But also we exploited quantum machine learning for this approach as well. Then portfolio optimization. Portfolio optimization, basically you have some number of the assets in your portfolio, and you would like to rearrange them, buy and sell, to make sure that you get some profit out of your portfolio. And quantum computing is beneficial here because you can investigate millions of possible combinations of portfolios to perform these computations, and you can get the values that you wouldn't be able to get with classical computer at all. Also, I can briefly highlight the model that allows us to design new drugs. This is something that can be interesting to people who work in healthcare area. Also, we worked on peptide design, and I guess we will come back to this work as well. Also, what you can observe from this paper, that if you would like to design peptides with some specific properties, you have to go through a huge, enormous space of solutions. And this space of solutions, will take huge amount of time if you will go through classical computation. You can go using machine learning. However, you wouldn't get that accurate results as you would get with exact quantum methods. Also, we worked during BMW Quantum Challenge on few problems like sensors position optimization, and we used some of the novel algorithms designed by our partners from Ivan Franko National University. That is totally a novel way to solve the optimization problems. And the same thing, like the similar algorithm, we exploited during the problem of optimization of production of test vehicles. Basically, if you have different cars with different components, you might want to test them in a different way, because some cars can be destroyed or not. And this is a very computationally expensive problem, and BMW spends a lot of money on this problem. That's why they would like to address this thing with quantum computing, because to perform those testings, they need to build another facility, and this is something that is very, very complicated and very expensive. So if you would like to talk to customers about quantum computing, please ask them what are the most resources and time-consuming problem that their business solves. what is the impact of this problem to be solved in terms of actual money, or in terms of actual like improvement of processes or whatever. And then we can think about how to help them, how to address this thing with quantum computing. I understand that there is a lot of information out there, but I think that we must stop right now. If you will see any opportunities, if you would like to ask any questions that go out of the scope of one small presentation with a few sentences, because it will be extremely hard to map everything that is done in quantum computing into one like 50-minute session, reach out to our quantum email. We can think about different kinds of workshops. We can just educate you on quantum computing, or we'll share some interesting stories on quantum. Do we have any questions?
So if you're also we end up with a presentation. Thank you for those dive into the world of quantum. We have a couple of questions from the participants on the workplace, and as well as in Zoom. The first question from Robert Kowalski. It was to the previous part of the presentation. The question was, why without quantum physics you won't have found the inventions like iPhones, solar panels, and he meant, what basis do we get from quantum to invent, produce them? Probably not the short question, but still, yeah.
Yeah, it's definitely not a very short question. So if we will, it doesn't matter if we'll come back to the slide. Basically, solar panels, they're using photovoltaic effect, and this photovoltaic effect is dependent on quantum physics, because energy is absorbed and in quantum packets. So basically that's the nature of this thing. Or if we're speaking about GPS, GPS uses quantum clock inside of that, and basically those are oscillations of the crystal, and those oscillations of that particular crystal, they have quantum nature. If we're speaking about lasers, that's also a result of the same thing, that you can have a coherent light, basically the light of a single color that goes out of the crystal. And the same applies if you try to make a lithography and you would like to make a microchip, you will still have to deal with quantum effects when you're doing them. And basically your transistors, they are that small, they are almost of the size of the atom, that you cannot neglect quantum effects out there. But if you would like to have a broader discussion, like, we can spend a few hours on this thing.
Oh, thank you for the brief answer. The next question from Vladislav Gudzenko. Do you have real commercial use cases, or there are just potential proposals?
So currently we have one big customer, not big, we have one customer that pays us money for quantum computing, and this is our partner. And this person works in, this company works in area of quantum computing. However, we don't do any production use cases right now, because quantum computing is technology. It's that is on the fourth horizon of technology, there to fourth horizon of technology. What we can offer here right now is research as service. We can help them to onboard to quantum computing. We can set their strategy to quantum computing. We can demonstrate the use cases that will make it valuable for them. But when I mentioned this use case of LA port optimization, we have all the instruments and we have all the knowledge to implement the state of the art within our team and sell it as the customer. The only thing that the results of that use case that demonstrated as production usage is somewhat challenged in quantum community, right? Among the people who actually perform quantum computing, and ourselves as well. So production is something that is in future. Concepts, roadmap, strategic innovation, this is something that we can do at R&D.
Thank you for the answer. So probably, yeah, the point of view for innovation for the particular company and the navigation tools, that's something definitely might be provided by your team. A couple of questions from Steve Gladstone. The first question is, are the best problems with quantum always parallelized?
Can you please repeat it? Are the best problems of
problems with quantum are always parallelized? So using parallelization to compute.
I wouldn't say so. It really depends on the problem itself, right? For example, some of optimization problems, they can be somewhat parallelized on HPCs using different approach, or on HPC clusters. You can address them that way, but some of them wouldn't be parallelized with that same efficiency. So I wouldn't think about quantum parallelization that has a totally different nature, and parallelization in traditional sense as you would do in traditional HPC. So it really depends on the problem itself.
Thank you. The next one from Steve. Also, would the problem if calculating fractals work on the quantum, or does the recursion interfere?
Let me think about that. First of all, I never looked into problem of calculation of fractals, right? So to answer this question, so I don't know whether it will work like on that or not. So I will have to come back to you with this answer, because like I never looked under this angle to this specific kind of problem. And if you see any application of this like fractal problem, please come to us.
Yeah, the small comment probably will share after the session would be good, if any, would be good to show a simple example of programming, showing gate setup and so on. Some thanks for the session. And a question from Eva Vaneva. Do we work on quantum computing use case for telco and media industries? And if yes, so what are those use cases?
Yeah, so for telecom industry, this is something that I mentioned. We would like to explore this area during next quarter, and in collaboration with Cisco, because this is something that deals with networking and with cryptography. So use cases that will be formulated there, they will be applicable for the telecom industry in general. But what we do in parallel, we currently building our new service offering. We go through the different use cases of different industries, and we've collected, I believe, almost 100 already by this moment. And different use cases, they can be mapped to very same mathematical problems. And for many of those mathematical problems, we already do have solution. The only thing that we need to find a proper use case that can be mapped to this thing. So if you have some ideas where quantum computing can address some problem outside of cryptography and networking, something that we are dealing with started dealing with already, but that will benefit for telecom. This is something that would be very, very interesting for us. Actually, British Telecom together with Toshiba, I believe, and HSBC recently launched quantum key distribution in UK. So yeah, definitely there is some offering for of quantum computing to that industry, but yeah, we need to work on that more.
Thank you. One more fun question, but I still ask them just to ask: do you use an S&P 500 predictions to trade in markets? Just some, I believe.
It was just for modeling purposes. Yeah, we just like use this thing as a case. Yeah.
Okay, and the last question: how much it costs? Probably the question is regarding the overall engagement process, or maybe or overall cost structure of implementing some research quantum project. I'm not sure. So Vyacheslav, if you can give any details that prompt us, it would be helpful.
So I will take the first thing that I understand, right? How much does it cost, maybe from perspective of utilization of quantum computers, right? For simple experiments that are usually subject of any concepts at R&D, you can use free IBM devices. Other than that, they can be really expensive, both IBM or IonQ or whatever devices out there. So for example, to construct very simple experiment that is relevant for finance using IonQ devices, for a single experiment, you will burn like $15,000 just for 2 weeks of experimentation, I believe. And this will happen really fast. So usually how we act, we have our partners, and our partners like AWS, they work with different hardware providers, and they can help us with getting some devices. So for example, if you would like to talk to your customer and speak that, okay, guys, would you be interested in exploring quantum computing? we can go and talk about some customers with our partners, and they can help with leasing the quantum device for this thing. This is something that usually works with NVIDIA or with AWS out there. Regarding the cost of people, I would keep it aside, right, basically, because like it's a regular type of engagement for SoftServe as it would be done for any other project. So the only unusual cost is cost of infrastructure.
Okay, thank you. The comment on top of your answer from Iva Veneva regarding telecom. Yes, British Telecom was the company for which I asked for. And the last question we have in the chat for right now from Steve. Yeah, air alarm is over. Yeah, so probably air alarm ended in Ukraine. So Steve Gladstone asks, how many qubits do we have access to?
It depends. We can have like on agreement, we can have access to up to 20 qubits devices through AWS. However, we had some conversations with IBM, and for Quantum Bootcamp, we had access to 127 qubits devices. But it usually just like if there is a matter of some problem that has to be addressed, it might not be the problem of big enough device to verify it. Because even for 400 qubit device provided by IBM, people had to pick subsets of qubits that will work with less error in the end of the experiment. So they try to pick much smaller subsets out of those 400s to make results like at least more valid and better for using in research paper or in their case that they're trying to solve. So for now, I wouldn't focus on the size of the devices, but like if needed, we can do it. For annealers that are different kinds of devices, you can have 2000 qubits if you need, or up to 6000 qubits if you need. The only thing that they will be able to solve on the optimization problems or satisfiability, basically all the problems that can be mapped to graphs.
Mm-hmm. Clear. So it depends. Do you have time to answer some more questions?
I do, yeah.
Okay, so probably for those one who is able to left for a couple of more minutes, it would be great. So the question from Oleg Bondarenko: do you know in Ukraine, apart from SoftServe, which other IT companies are engaged in researching the possibilities of quantum computing?
In Ukraine, I would say that those are not companies, those are institutions, right? Research institutions or universities. Also, there is a brilliant company that is called Haiku, and you might Google about this company. But I wouldn't say that any of big companies that act in Ukraine currently investing significant efforts into quantum computing. However, globally, companies that are even similar to our company, like Capgemini or Accenture, they are doing quantum, and that's important part of their like R&D strategy.
It's really great to be in forefront, especially in Ukraine. So one more question from Pavlov Robets. Have you already tested standardized quantum algorithms like Falcon, crystals, and so
on? No, not yet.
Not yet.
Devices, right? Not the algorithms.
The question was about quantum algorithm, but probably it's related to the hardware. I'm not sure.
Because I thought that those are names of the hardware pieces provided by IBM. Sorry, like Eagle, or maybe I'm just yeah. So like Falcon and Eagle. So yeah, we had access to Eagle device during the bootcamp.
Clear. So that was the last question in the chat. If there is any you want to ask, you can jump into right now, or also drop in the chat.
I wanted to comment about one of the questions that we missed, like showing gates and circuits. If you want to have more gates or circuits, it depends on what you would like to achieve from like this kind of seminar, right? If you want to educate in general in quantum computing, it won't be enough to show just a single circuit and show how, like, what will be the outcome of the circuit and how qubits are working. And most likely it won't be interesting to a wider audience. However, we have quantum webinars that you can join, and you can see what are research updates happening inside of quantum team, what are the actual research problems out there. And also, if you need some recommended materials, how to understand quantum, yeah, also please feel free to reaching us.
So that's it. Seems like there is no question. If any more, you can reach out to the Miran teams to just have an educational conversation or to like kick off the navigation process with your customer. And thank you, Demir, for your time today. It was really nice and interesting to dive into the quantum industry, quantum physics, and its current and potential application, and have SoftServe staying in the forefront of those of those technology.
I would maybe, sorry, just add a small comment. If there is demand, right, in showing more industrial side of things, we can make a second session explaining how quantum maps industry in more detailed way, because it's hard to speak about quantum, what quantum means, and how quantum computing works, and then how to map it to real life. It's too much content for a single session. So if there will be demand, just like let's make a second session on just focused on different industries and aspects. But before that, I would like to hear from you. You are working in different industries. Let's have a talk. Let's try to understand what we can do with like for your particular industry. Let's brainstorm. We can, like, if you're in Wrocław, let's talk in a room and discuss it.
Yeah, sure. Probably till the time you will have the point of view and the updated content on our like channels. Thank you. Thank you, everyone who's joined today. Have a good day.
Thank you. Bye.
Bye-bye.